Welcome to the lesson on rationalizing the denominator. So, what does rationalizing the denominator mean? Well, hopefully you know that rationalizing means basically means no square root. Right? So a square root would be what we call a radical, and we want it to be rational, meaning no radical. So no square root. So what this means is when you get a number, so maybe you're solving a problem and you end up with your final number or answer, it looks something like that, 3 over root 7. Just sort of as a convention, we don't like this. We don't like that the bottom is not rational because there's a square root, the bottom being the denominator. So as a convention, we're just going to get rid of that square root on the bottom. So how do you do that? How do you turn root 7 into not a square root? Well, you can multiply it by something. You can multiply it by root 7. But now I've changed the answer, right? If you multiply the bottom by root 7, you change the answer. So if we want to maintain the same number, we have to multiply the top by root 7 too. So this thing right here is just equal to 1, so it's okay to multiply this by 1. So you'd end up with 3 root 7 over root 7 times root 7 is just 7. And then that's how you're going to leave the answer. So 3 root 7 over 7. So now notice there's no radical in the bottom. So that's the way we like it. And it's just going to make your answers consistent. So if you check the back of the book, when you're doing a harder problem, you know you're going to get the same answer as them. Let's try another one. Let's say it was something like 9 over 2 root 3. So now notice the denominator, the whole thing's not a square root, just the root 3. We have the 2. So all we really need to get rid of is that root 3. So you don't need to multiply by the 2, you just need to multiply by root 3. And then the same thing on the top, whatever you multiply by the bottom by, you have to do the top by. So you have 9 times root 3, 9 root 3, over 2 times root 3, 2 root 3 times root 3, I mean. So that'd be 2 times, and then root 3 times root 3 is 3. And now you can multiply the 2 times the 3, but you might also notice that 9 and 3 have common factors, right? 3 goes into each, goes into 3 once, and it goes into 9 3 times. So you end up with 3 root 3 over 2. Alright, so that's what we mean by rationalizing a denominator. Now it can get a little more complicated if we have what we call a two-term denominator. So two-term denominator. I guess I forgot to spell the whole word. Okay, so in order to deal with a two-term denominator, I'll show you what that means in a second. We're going to need a concept of what we call a conjugate. Conjugate. So a conjugate, well, I'll just write an example. So the conjugate of any two terms, so conjugate, let's say you have A plus B. So there's two terms, right? A is one term, B is another, and we're adding them. Then conjugate is, instead of A plus B, the conjugate would be A minus B. So that's what a conjugate means. It means, you have two terms and then the opposite sign in the middle. So if it's plus, the conjugate is negative, and then vice versa. So the reason that this is important is when we do the product of conjugates, something sort of important happens. So if I multiplied A plus B times A minus B, if A times A, A squared, A times minus B, minus AB, B times A, plus AB, and then b times minus b is minus b squared. So notice the two middle terms have opposite signs, so they cancel out. And that's always going to happen with conjugates. And that's what's sort of important about the conjugates, that when you multiply a conjugate or two terms by its conjugate, the middle terms always cancel out. So we'll see why that's useful right now. Well, let's do an example. So let's say you had a radical on the bottom of a expression, and it was two terms though, so like root 2 plus root 5. Well, now the question is, what can I multiply this by to get rid of the square roots? And given the discussion we just talked about, probably suggests your conjugate. And then the same on the top. So the conjugate of root 2 plus root 5 is root 2 minus root 5. So why do we do that? Okay, so we're going to have 3 times, and I'm not even going to bother actually expanding this 3 in here. And you'll actually see why in a second. But then when I multiply the conjugates, notice root 2 times root 2, just 2. And then remember the middle terms will cancel, so we're just going to have minus root 5 times root 5 is 5. So what happened was we got rid of the square roots on the bottom. So that's kind of the whole point of multiplying by the conjugate. It'll get rid of the square roots all over, and then notice 2 minus 5 is minus 3, and then we have common factor here, 3 and minus 3. So that's why I didn't bother multiplying it in. So you end up with negative root 2 plus root 5. And notice, I'm hoping no one is thinking that you can add those together, right? If the thing under the square root is not the same, you cannot add them. Okay, so that's a good example, and then let's just do one more. Root 6 over, let's see, here's a good one, 2 root 3 minus 1. So again, there's a square root, and it's 2 terms, so that means you have to multiply by the conjugate. So the conjugate is 2 root 3 plus 1 over 2 root 3 plus 1. So up here on the numerator, 2 root 3 times root 6. Remember how to multiply square roots, that would be 2 root 18. You multiply the numbers under the square root together, plus root 6, all divided by, okay, so 2 root 3 times 2 root 3. Multiply the outside numbers, 4, and then the square roots, 3. And then the middle terms will cancel, and then minus 1 times minus 1. Or plus 1 is minus 1. So you have 2 root 18 plus root 6. Now something unique about this square root here, notice there's a perfect square that divides 18, right? 9 divides it, so the square root of 9 is 3. And then what are we left with? 2, right? 9 times 2 is 18, but we have 3 because we took the square root of 9, plus, and then you can't do that with 6, so we'll just leave it as root 6, right? No perfect squares divide 6, all divided by 4 times 3 is 12, minus 1 is 11, and I mean that's pretty good. You might go ahead and multiply that out. But that's pretty good, right? Now we have no denominator on no radical on the bottom, so we're good. Yeah. So that's the concept of rationalizing the denominator. Basically, it's just a convention. You can kind of think of it like reducing fractions, right? You always want fractions in lowest terms. Same idea. You never want a radical in the bottom.